Okay, so we have examined the graphs of logarithmic and exponential functions, and now we're going to talk about properties of logarithms and being able to solve logarithmic equations. So remember what we already know about logs from Module 12. Log base A of x equals y, that converts into a to the y equals x, right? So we have this logarithm property. We have a being a base value, and then this x, whatever we are taking the log of, we call that the argument. Okay? So property 1 here says as long as we're dealing with a log and the base is greater than 0, positive, the base is not 1, and the x and y are positive in all of these examples. So log base A of 1 is always 0. And if we think about converting, what we know, that would be the same as saying a to the 0 equals 1. So an example of this might be log base 2 of 1 or natural log of 1. Common log of 1 and, log base pi of 1. All of those, it doesn't matter what the base is, when you're taking the logarithm of the argument 1, your output is going to be 0. Property 2 here says when the base and the argument match, the log is always going to equal 1. And again, thinking about how we said that we can pull that in there. The logarithm is a power to which we raise the base to get the argument. This is the same as writing a to the 1 equals a. So some examples here. Log base 2 of 2 is 1. Log of 10 is 1. So dealing with a common log, that's base 10. Natural log of e is 1. So a natural log is base e. So the base and the argument match there. Or log base 5 of 5 would equal 1. So continuing down, using our chart here, composition of inverses. So these are both very similar, 3 and 4, but when you have a base with a logarithmic power of the same base, or a log with an argument that is the same base to the power, they're going to cancel each other out, and you'll just end up with that argument x as your answer. So an example of this might be 2 log base 2 of x would equal x, or e to the ln x would equal x, because in both of these two examples, the exponential base and the logarithmic base match. Similarly, if we were taking the natural log of e to the x, that would equal x, or the common log of 10 to the x, that would equal x, or even just log base 3 of 3 to the x, that would equal x. So we have this property that simplifies our logarithmic and exponential equations nicely. They come in handy when we start talking about solving equations. Okay, we have 3 more properties here. We have a product property of logs. So if you have 2 logs that have the same base and you're adding them, the new argument, we can condense them together, and that new argument would be the product of those arguments. So an example of this might be natural log of 2 plus natural log of 3. And that would equal natural log of 2 times 3, or 6. Another way we could think about this would be if I wrote log base 2 of 4 plus log base 2 of 8. So again, we're adding those two logs. That's going to equal log base 2 of 32. And if you think about it, log base 2 of 4 is equal to 2. Log base 2 of 8 is equal to 3. And log base 2 of 32 is equal to 5, because 2 to the 5th equals 32. 2 cubed equals 8, and 2 squared equals 4. All right, our quotient property of logs, which says basically the log of a quotient is the difference of the two logs, or if we have a difference of two logs, we can take the arguments and write them as a quotient. So here we might have the natural log of 12 minus the natural log of 6. And that would become the natural log of 12 over 6, which is equal to the natural log of 2. And then our last property on this page, when we're dealing with the power rule, what we can say is that when we have a log and there's something raised to a power in the argument, that power can come out in front and be multiplied. So for example, if we had log base 2 of 4 cubed, that would be the same as saying 3 times log base 2 of 4. And you can check that this is true in both situations. 4 cubed is 64. So this says, log base 2 of 64. 2 to what power equals 64? You'd say 6. And on the right side, log base 2 of 4, that says 2 to the second power. So the 3 times this value becomes 2. So that checks as well. And being able to properly use properties of logs is going to be really super important when we start talking about solving equations with logarithms in them. So continuing to the next page, we've already talked about this property, but this is our conversion formula. This is how we convert from log form to exponential form. And I mentioned this in the last video, even though it wasn't there yet, change of base formula. So in order to type a log into your calculator that is not base 10 or base E, and as we've also mentioned, you've got two buttons on your calculator. One says log, it's got a 10 to the x over it. That's your common log base 10. And the other one says ln, it has an e to the x over it. That's your natural log base E. And so those little values that we can use as an option when we're typing, those are also there to kind of help you remember what base your calculator can type for different logarithms. So in this situation, an example of this might be if I had log base 2 of 5. I can't figure this out on my own. I'm not sure how to do it by hand. So what I can do is I can take the common log or the natural log of that argument over the base. So the two ways I could type this into my calculator, natural log 5 over natural log 2, or common log 5 over common log 2. Those would give me both the exact same value. And that value, when we type it into our calculator, we get approximately 2.321928. You round wherever you want. Okay, so here looking at our notes, we've got two situations where we're going to use the change of base formula. I personally just prefer to write ln, so I'm going to use that. But again, you could use that common log property twice. So if I wanted to do log base 2 of 10, I'd type that into my calculator as ln 10 divided by ln 2. And doing this, I should get approximately 3.32. Or say, for example, 2 log base 7 of 52, that would be ln 52 over ln 7, which gives me approximately 2.03. You had the option to use common log when setting up this expression as well. You just have to make sure you're consistent and that you use the same log button in the numerator and the denominator. So if we wanted to graph something in our calculator that is not base 10 or base E, here we have base 5, we have to use the change of base formula. And so in this case, I would go to my y1 and I would type in ln of the argument, x plus 3, divided by ln of the base, which is 5. You could also use common log. They'll give you the exact same thing. And what you'll see is this is the graph of a logarithm base 5 shifted to the left 3 units. It looks roughly like this. And we have a vertical asymptote occurring here at x equals -3.